Hello everyone, welcome to the last session of this week. So in this session, we will use a MATLAB built-in PSO function to solve a real-world engineering case study. So what we are going to do is to optimize the control parameter of a PID controller. So let's see about the details about the problem. First, what is PID controller? The PID controller, we call it a proportional integral derivative controller, right? So this kind of control method is widely used and has a long history. So for example, in real world, we can control many things. So for example, we can control the temperature of a component, or control the elevation of a lift, or we control the flight altitude and speed of unmanned aerial vehicle, right? So the control flow is like this. So we can see this is quite complex, looks like. So we have an arrow here. This is a controller itself, and we have the output, and we have a controlled object. So this is called system output. So you don't really need to understand this, right? So because this is done by the control engineer, but you need to understand, so what are the design variables that you need to optimize, and what is the objective function. So the objective function here, we want to minimize the total error. And this total error is related to this ET. So this ET is what is a system output and the given error by the user, the difference of that, right? So we can see here is an example of a hydraulic lift of using PID control. So for the PID controller, look into more details, we can see this is a control function. So you can see there is a KP, KI, and KD. These are the control parameters that we want to optimize. Like we just said, there is an ET, but we don't really optimize the ET at a certain time t. We optimize the integral of error in a period of t. So this is J is the objective function. And we can write the J, KP, KI, KD. So objective function related to these three control parameters. And we want to do minimization to this, right? So how to make this PID control? If we can use MATLAB's Simulink. So Simulink is another MathWorks product. So in parallel with MATLAB, when we build this control system in Simulink, this is a PID controller. So now based on this one, we can write the optimization problem and the objective function. So we can see like that. We want to minimize Jx subject to considering three key control parameters. Each one has a search range. Then we can see the objective function is here, the function called PSO underscore PID. X is included x1, x2, x3 are the three parameters, right? So we can, this lift underscore PID is a Simulink system, right? So we can put into them, and we can do the simulation. And here is the objective function. So this is a function to be minimized. So you don't need to understand these details. You only need to understand what are the decision variables and what is the objective function. So we can see the live script for more. If you are interested, you can try it yourself. Then we will carry out the PSO optimization of this PID control system. As we can see, I first use optim options. We set several things to the PSO optimizer. This one, we want to get the convergence trend, right? The swarm size, we say, okay, 10 individuals or 10 particles. Maximum iteration is 20, so I don't use parallel computing. This is the lower bound, the upper bound, three design variables, and we can put at, this is the objective function. We use a format that the particle swarm function that we have introduced before. So this tip and top means we will get the runtime of this optimization. So after we execute this program, we can find this. So the convergence trend is plotted here. We can see the base function value is 8.07, quite a good value. So x is optimal value of the 3 control parameters. And we can see the elapsed time is 287 seconds. So you can try it yourself in the live script. Now I do some change. So let's see where is the difference. So the difference is here, right? Previously, I don't use parallel computing. Now I use parallel computing. So I said use parallel equals to true. Now we see what happened. The optimization process is here. Best value is same, and we get the same optimal solution. But we can see here, the elapsed time is 1/3 of the previous one. So you can also try this in the live script, right? So in this session, we use a PSO built-in function to optimize a real-world engineering problem, right? Okay, so that is all for this session. Okay, thank you very much. Bye-bye.